I want to give you some additional notes on how we can estimate the runtime performance of algorithms. One of the topics we dealt with in Module 6 consisted of uh, sorting and searching, analyzing the performances of algorithms that would sort an array of data elements or search for a data element within an array of data elements. And as we looked at the content of this module, we noticed that there were several implementations for these types of these types of computer tasks, and different implementations had different performance characteristics. And one of the key performance characteristics was the amount of time it would take, say, to sort a large array or to search for an element in a large array. So um, essentially, because you have a multitude of choices for selecting a particular algorithm, you obviously want to make a choice where the algorithm has um, the best runtime performance. And so uh, um, one of the things then we would like to know then is to how to uh, calculate the running time complexity of an algorithm. Obviously, if you proceed to develop algorithms for a client, you want to give them the one algorithm that has the best possible runtime. So to do this, we use asymptotic notations. Okay, um, these are formulae which compute the upper or lower bounds of execution times for a given algorithm. So I'll explain. All right. So the first type of asymptotic notation we have is called the BigO notation. And so let me show you how BigO notation is used to assess the performance of, say, a sort or a search algorithm. So written as BigO calculation. All right. So in terms of a graphical depiction, suppose I have, say, a graph that looks like this, where I have two functions. Let's let this axis be called the theta axis. And let me give you a graph that looks like this. And let's call this graph g of theta. So g of theta looks either parabolic or exponential in form. And let me overlay on top of this graph another graph. Let's call it f of theta. All right. If you notice that there's a threshold where the two graphs intersect, for which, as theta increases, beyond this particular value of theta, we note that g of theta always is bigger than f of theta. So what we say then is that the big O of f of theta is equal to g of theta. This means that for input values bigger than theta, f of theta will be dominated by g of theta for all values of those thetas. Right? So the next kind of comparison we want to do when comparing the runtime performance of an algorithm is called the omega notation. So we call this omega notation. And what does this mean? Again, I'll use the graph analogy. So here's my graph. Instead of using theta, how about I use n? And informally speaking, we can say that n represents, say, the number of elements that you're sorting or the number of elements which you have to search through. All right. So again, let me graph a particular function. This time I'll call it f of n. All right. And overlaid on this graph, I'll have another graph which I will call g of n. And notice that there's a threshold value of n. So for all possible values of n bigger than this particular threshold right here, we note that f of n is bigger than g of n. All right. So in this case, we say that the omega of f of n is equal to g of n. Another way of stating this is that g of n is a lower bound. For f of n. All right, now let's go back to slide 1, or slide 2 that is, and let's discuss this in terms of an optimization vantage point. Now, for the BigO calculation, we see that uh, uh, g of theta, in this particular case, dominates f of theta. And so this is called the upper bound. So g of theta is an upper bound. Now you may ask yourself, well, is this upper bound unique? Well, with BigO, and that's one of the purposes of BigO notation, is to establish the uniqueness of this upper bound. It turns out that g of theta is actually a least upper bound. All right. Even though there are many possible functions that could be bigger than f of theta on this particular range, right here, g of theta is the one for which there are no other functions which will lie below it. Okay? If you pick another function that lies below g of theta, it will also lie below f of theta. All right? So there are no other possible functions that could lie below g of theta. So in other words, there's nothing that would come across like this. There's no other function that could be found which would fit in between g and f of theta like this. So of course there are functions that would lie above g of theta like this. We could have functions that lie above right here, but the fact that g of theta is the least one makes it the least upper bound, and this least upper bound function, if found, is known as the big O of f of theta. So now going back to slide 3, the converse essentially applies. We see that f of n, the function f, lies above g of n, but g of n is the biggest lower bound for f of n. All right, so we say that in this particular case, g of n is the greatest lower bound. All right, that's what we mean by the omega notation. In other words, there's no other function that lies between f and g of n that can be found. So there's no other function that you can insert in between and call that a lower bound for f of n. So g of n is bigger than any other function that could lie below f of n. So admittedly, there are an infinite number of functions that lie below g of n, like so, but g of n is the bigger, lies above all of these other functions, and there's no other function that lies between f and g of n. And that being the case, we say that f is the omega of f is g, and it's a greatest lower bound. All right, now also mentioned in your text is theta notation. All right, so what theta notation basically is, it's a combination of big O and omega notations, right? So what is it? Theta notation. All right, and so what theta notation means is that you find the least upper bound and the greatest lower bound for a function. And it goes like this. So again, we'll draw our graph. And we say that, okay, so here's our f of n. I'll draw in red like so. And then there's another function, which we call g. And g will look something like this. Okay, so here's our g. So this will be our g of n. And here is our f of n. Okay, now what's interesting is that you can also have another function. Let me call this g sub 1. Okay, and let's overlay onto this graph another function which I will call g sub 2. So I'll call this g sub 2 of n. All right, and then we could say that, okay, here's a threshold. Okay, and so for any value of n bigger than this n hat, we see that f of n is confined between g1 of n and g2 of n. It doesn't go above g2 of n, and it doesn't fall below g1 of n. So let's define a piecewise defined function. Let's say we have a function called g. Okay, and so g is equal to say g2 of n. So let's see here. What's a good way to express this? No, let me check that. Let me take that back. Let's say that we know that trying to think of a good way to explain it. We say then that let's let how can we represent a function being banded? We say that g1 of n. Okay, so let's write this. We say that g1 of n, of course, is equal to big O of f of n. right? And then we say that G2 is equal to omega of F. So if you have this case, uh, if you have this particular case, then we say then that if you find two functions, okay, if you can find two functions, so we'll say that I'm trying to think how we can express this notation here. Let's let let's let oops, what happened? Let's let okay. So we got kind of a peculiar type of functional arrangement here. So let's let uh, under a particular circumstance, let's say, okay, let's let, all right, I'll tell you what, it's a little bit confusing in the book, but we say that if we can find, why don't we do this? If we can find such two functions, if we can find these functions G1 and G2, then we have, we'll call it theta of F, okay? So if you can find those two functions, one being the greatest upper bound, the least upper bound, excuse me, the least upper bound, and the other being the greatest lower bound, you can find two functions for the given uh, function f, then we say that we have those two functions would be the ones needed for the theta of a given function. All right, so that's the theory um, behind the asymptotic notations of the runtime complexity of an algorithm. So let's back this up with some examples that you've been working on this week. So let's talk about the selection sort performance. So let's see, pull up a test. Selection sort performance. All right. So let n equal to the size of the array you are trying to sort. We want to find the smallest The first thing you want to do in a selection sort is find the smallest of the n element array. Okay? So to do this, we need to visit n elements. Okay? So when we find a choice for the smallest element, we swap the elements if necessary, which takes 2 visits. In the next step, visit only n minus 1 elements to find the next smallest element in the data array. Okay. 6, next, visit only n minus 2 elements to find the next smallest element. Okay, so we keep repeating this. All right, keep doing steps, keep repeating this method until finally we say in the last step, visit only 2 elements. So what does this mean? Okay, so from an algorithmic perspective, the total number of visits. So what is the total number of visits? So we traverse the array, we identify the smallest element, and then we swap. We swap the elements, okay? So the total number of visits is all right, so what is this number, or the formula for this? Well, it would be n plus 2 plus n minus 1 plus 2 plus, and so forth, plus 2 plus 2. Okay, and so when we simplify this sum, we will have n plus n minus 1 plus 2 plus n minus 1 times 2 visits. Right, the total number of visits when we hunt for the smallest element, and then we do the swapping and so forth. All right, we can further simplify this, and I won't go through the algebraic simplification, but turns out from algebra that this formula is actually equal to something that looks like this. And this can be proven mathematically. All right, and when we add these three, when we add these 3 terms together, we get a formula that looks like this. Now, n is the number of elements in your data array. All right, and so this is the number of visits that are required to do a selection sort in your data array. Okay, this is the greatest upper bound, or the least upper bound for the number of visits required to do a selection sort. All right, so what this formula tells you is that you don't need to exceed the output of this function the number of visits required to sort an array of size n, where the n are the number of elements. All right, so what does this mean? All right, so how do we interpret this information? All right. So for large n, all right, so let me write the formula again. So the formula is 1/2, it's this quadratic formula, 1/2 n squared plus 5/2 n minus 3. Now, suppose we have a million elements. If we have a million elements, what happens is that these two terms become inconsequential because 1 million squared is very much larger than 5/2 times a million. So we say that because this term in the quadratic dominates, the number of visits is of order n squared. Okay, and so now this is an upper bound estimate, n squared. All right, and so we say that the selection sort algorithm for an array of size n is big O of n squared. All right, so um, even though the execution time of your selection sort algorithm for an array of size n will probably be less than this particular formula, nevertheless, the execution time will be dominated by n squared. Right, so we say that this is big O n squared. So what does this mean in terms of performance of your algorithm? Well, it turns out you make these kinds of considerations. Here's the takeaway basically from all this theory. If an array size doubles, if your array size doubles, what would happen to your performance? How is performance affected? Because ostensibly, your programs are written to handle any ad hoc type of input. So you never really know what the size of your arrays are going to be. Okay. So for instance, you give your program to your selection sort, you give your selection sort program to a customer, and the customer inputs 1,000 elements to be sorted, and then the next week your customer has 10,000 records to be sorted. So what would be your customer's feeling about your use of selection sort to sort these data? So in this case, what happens if the your customer doubles the size of an array to be sorted? Well, it turns out with BigO notation, we originally had n elements, and now we double the size of the array. Okay, and so with the selection sort, we have selection sort. We just proved in a very sketchy format, the selection sort is dominated by n squared. And so now what do? All of a sudden, we double the array size. And so now the new array will be dominated by this. Okay. And so basically the runtime, the upper bound for the runtime will be 4n squared. Okay. So what this means then is that we have a fourfold increase, oops, should spell that right. Fourfold. Increase in runtime. All right. Now, if this were a bank, okay, a large bank, and they're doing month-end processing to send out statements, savings account statements to the customers. Suppose at the start of the year, the bank had 1 million customers, okay? And so in calculating the savings account statements, they may have had to done a sort. And at the end of the year, the customer base of the bank doubled to 2 million customers. All right. Now, to sort 1 million records with selection sort, perhaps it took 2 hours. Okay. Now, with the doubling of the clients, the customers, the bank, the computation would be 8 hours. So going from 2 hours to 8 hours, you would have to assess whether your client can tolerate that, especially if they're paying staff to operate this program. At 20 bucks an hour, so instead of paying, $40 to print out or run the statements processing, it now takes $160. So you've seen your labor costs go up considerably, and not only that, your execution costs. So this can be kind of expensive. So it's definitely something to consider. All right. So that would be the idea behind selection sort performance. So the other type of sort that you worked with was the merge sort. So let's see if we can attempt to analyze the runtime performance of merge sort, and then we'll compare merge sort performance with selection sort performance. All right, so with merge sort. So, all right, so with merge sort performance, we must estimate the number of array element visits that are required to merge, sort an array. Assume the first and second halves of the array have been sorted. Right? Each step in the merge process, each step in the merge process adds one more element to the final sorted array. That element comes from the first or second arrays, first or second array, and the elements from the two halves must be compared. This requires 3 visits. One for the final sorted array, which we call A, and one each from the 2 array halves. This is 3 n visits. So for an array of size n, this is 3 n visits total. All right. Now, moving on. Moreover, we had to copy elements from the original array, which we call A, to the 2/2. Okay, so we have to account for this. This yields another 2n visits. This yielded another 2n visits. Okay, thus 5n visits were required. To move data from the 2/2 to the final sorted array. All right. Okay, so moving on, step 3. Let Tn, okay, again, this is a function, define the number of visits required to sort a range of n elements. All right. So keeping this in mind, to sort the 2/2, okay. All right. So we'll have to sort the 2/2 and then merge them back into the final sorted array. So I guess I can continue on here. All right. So to sort the 2/2 and merge, the least upper bound estimate for the amount of visits required would be this formula. Okay, the sort time, it would be the time to sort and copy the first array plus the time to sort the second array. Check that. Tn is the time to sort. Okay. Tn over 2 is the time to sort the first array. Tn over 2 is the time to sort the second array. And then 5n is the time or the number of visits to copy the data from the original array to the 2/2. All right, so we have this formula. Now, if n is odd, okay, if n is odd, we of course wouldn't have n over 2 here. But since we're dealing with estimates and least upper bounds, add 1 to it. Add 1 to make it even so that we can continue on with this discussion. There's no loss in generality and just adding 1 more visit to the value of n. Okay. Now, suppose so now we need to calculate what Tn over 2 is. All right. Because this is now a recursive like formula. All right. So what is Tn over 2? So let's do that. Let's calculate Tn over 2. All right. So we have Tn, I'll rewrite Tn again, is equal to Tn over 2 plus Tn over 2 plus 5n. All right, so Tn over 2 then, through algebra, is equal to is it Tn over 4 plus Tn over 4 plus 5 halves n. Okay, and so that's just equal to 2 times Tn over 4 plus 5 halves n. All right, so now we need to calculate what Tn over 4 is. Okay, well, before we do that, we can state that this is the formula for T of n. So T of n is equal to 2 times Tn over 2 okay, plus 5 halves. Let's check that 5n. Let me see. Let me check. Yes, plus 5n. Okay. But now we take this value of Tn over 2 and we replace it with the value, its representation in over 2Tn over 4 plus 5 halves n. So this is equal to, I'm going to substitute in that equation, and so I will have 2 Tn over 4 plus 5 halves n plus 5n. Okay, and that is equal to what? 4Tn over 4 plus 5n plus 5n. All right. Okay, so we have, so this would be the number of visits required for a merge sort with n elements. Now, so we need a formula now for this, right? Tn over 4. So what is Tn over 4? We have to solve for that. Well, proceeding as we did before, we have Tn over 4 is equal to 2Tn over 8 plus 5n over 4. And again, we'll substitute that back into our formula for Tn. So T sub n then, in terms of n over 4, would be 2 times 2 times 2 T n over 8 plus 5n plus 5n plus 5n. All right, so this can go on for quite some time. As a matter of fact, it could go on forever. So what if we came to the conclusion for all of this substitution and noted that we could reformulate Tn in powers of 2. All right, so if you observe the trend, we can reformulate the number of visits for the merge sort algorithm in powers of 2 to look like this. It's actually written as this formula. Okay. Okay. So as k grows large. Okay. So k is some large number. So if n is a very large array, then k is basically a number, an index, which determines the number of visits. So ultimately, you want k to for extremely large arrays, k is going to be a very large number. So it turns out that k, if we let n equal to the k. Now this is kind of a big assumption. So n, of course, in reality, n will not be 2 to some power. N is the size of your data array. But choose k so that 2 to the k is the next power of 2 that's greater than n. Okay? So for instance, if n is, say, 58, then k would be, what, 6, right? Okay, because 2 to the power 6 is 64, and so we'll choose n to be 64. So instead of using a hardwired number of 58, we'll just let n equal to 64. And this will basically be the formula for your least upper bound. So this is your least upper bound. We'll call it the LUB. This is your big O for merge sort. Least upper bound. Okay? All right. So now we can make some further simplifications. With this assumption, let me open up another page. All right. So if we cap the choice of n to be the next power of 2, so if we let n equal 2 to the k. So instead of having some precise number for n, we'll cap n to be 2 to the k for our estimate for the number of visits. So the formula was, okay, and I'll rewrite it here, t to the n is equal to 2 to the k. Again, we're only trying to get an estimate for the maximal runtime. Plus 5nk. Now, if you remember from algebra, let's go back to this formula. Okay, we can solve for k here. Okay, and it turns out that, of course, k, and I'm not going to go into logarithmic theory. I'll assume that you know this. If not, you can look it up. K is equal to log base 2 of n. All right, and so solving for k, in making the substitution n equals 2 to the k, the formula for t to the n becomes this. So 2 to the k right here, that is equal to n. Okay, and since n is 2 to the k, 2 to the k over 2 to the k is 1, plus 5 n log 2n. Okay, so this would be the number of visits required for an n size array, the upper bound. So this is the least upper bound for the number of visits required to merge sort an array. So LUB required to merge sort. And by this I mean n is the number of visits. N is array size. And T of n is the number of visits. what the book calls number of visits or operations. Okay, and there's a lot of theory about what an operation is, but it's beyond the scope of this book right now. Okay, so now this would be hard to oh, and I guess I could simplify it even further since t to the 1 is just 1. The time required to do one visit is just 1 unit, okay? So we can let this be units, so further simplifying, we get this. Now, this is hard to calculate on your calculator because in general, your calculator doesn't have a log base 2 function. But it turns out if you are really good with logarithms, okay, the log base 2 of x, okay, from your algebra, which you probably don't remember, but no worries, I'll give you the formula, is equal to the log base 10 of x over the log base 10 of the base, logarithmic base. So this is how you would calculate log base 2 on your calculator. All right, and log base 10 of 2, which you can do on your calculator, this turns out to be approximately 3.32 log 10. So now you have a means of calculating the number of operations required to merge sort an array of size 10. All right, so now we have a conclusion. We're getting close to a conclusion here. All right, so T of n is equal to what? N plus 5 n times 3.32 log base 10 of n. Okay, which is equal to n plus what? Oh, we'll just say 16. Approximately n plus 16 log n. All right. So what is the dominating term? Okay. Well, oops, I forgot. Check that n log n. All right. So for large n, log n is bigger than 1. Okay. So this, for large n, this factor becomes much bigger than 1. So the dominating term is the dominating term is n log n. All right, so merge sort is big O, okay, of n log n. And so we just did a kind of a formal computer science proof. All right, so using this, we are now in a position to compare the selection sort with the merge sort, the performance, okay? So let's do that, all right, which is kind of the critical point or the essential point of this discussion. So let's compare merge sort performance with selection sort. All right. So we know that the merge sort is a big O n log n. And the selection sort is big O of n squared. So how can we use these two big O notations to compare? Well, um, suppose we sort 10,000 records. Okay, so we first sort 10,000 records, 10 to the fourth records. Then your customer comes along and says, well, I need to actually sort 1,000,000 records, right? Then we sort. So which solution will you give to your customer? All right. Well, consider the selection sort. All right, so the increase in runtime for selection sort will be something like this. Since we know selection sort is big O of n squared, all right, so we have this increase in runtime. It will be, since we have to take 10 to the fourth times what? 10 squared equals 10 to the 6th. So we have 100 times more data to sort. And so in terms of the visits, or in terms of the runtime performance, we will have this increase in runtime. Okay, and so that would be, what would that be? That would be 10,000 times. Okay, so this would imply 10 to the fourth times longer. That is substantial, right? So if it took, so to sort, to merge sort, I'm sorry, check that. To selection sort an array of, say, I don't know, 10, suppose it took like 5 minutes. Okay, so it took 5 minutes. No, not, wait, that's too long, right? Suppose it took 1 minute. Suppose it took 1 minute to sort 10,000 elements. Well, then you go up to 1,000,000 elements, then it's going to take 10,000 minutes. So that would be huge. That would probably be completely unacceptable to your customer, going from 10,000 to 1,000,000 records, taking 10,000 times longer. So 10,000 minutes to sort 1,000,000 records. That could be days, right? I'm not going to go into how many hours or days that is, but 10,000 minutes would probably be a deal breaker if you're bidding on business for this particular customer. All right, so does merge sort offer an improvement? All right, so let's do the same comparison with merge sort. All right, so again, 10,000 minutes, okay? Keep that filed away somewhere. All right, so we know that um, merge sort is n log n in performance. BigO in log n. All right, so again, we're going from 10,000 records to 1,000,000 records. So what would be the performance comparison there? So with n log n, okay, so the ratio would be what, 10 to the 6th log 10 to the 6th divided by 10 to the 4th over log 10 to the 4th. If I did this right. And so this would equal to 100. Now, log 10 to the 6 is just 6. Check that. I'm sorry. Yeah. 10 to the 6 over 10 to the 4th is 100. Log 10 to the 6 is 6. Log 10 to the 4 is 4. And so that would be 3 halves, right? So this would be 150. So if the merge sort took a minute to sort 10,000 elements, and then you increased your array size to 1 million, then it would take 150 minutes. And of course, this is much more improved than 10,000 minutes. So 2.5 hours versus 10,000 minutes would be a substantial gain in time. And so your customer would probably be more pleased with this. So here we go. This would be the basis of comparison of merge sort with um, with a selection sort. Now, again, this this lesson was this note was very sketchy in terms of the explanations. That's as detailed as your text goes. So if you have any questions, by all means, feel free to email me or post or call me, and we can talk more about this. Um, and also, I noticed that you guys made some, for Module 6, you made some very good initial posts. I appreciate that, and they were all on time. Um, I would like for you to respond or reply back to two of your other colleagues. I noticed during the course of this term, you guys haven't really been talking to each other, and so bear in mind that talking to each other is a requirement for this class. So I'd like to see more interaction between the four of you guys, um, just replying and making comments or suggesting new things. Let's see that. Let's try and beef that up again. So yeah, so we'll go ahead and conclude it, this particular video, and I'll see if time permits, I'll make some more.